This is the 18th episode of Advanced J1939 for Technicians. In this episode, I'm going to discuss uh, what a bad ground or a ground with excessive resistance looks like to the CAN bus, what it would appear as on the oscilloscope, and what you would and then cover the theory of that with Circuit Lab here first as to why we see what we see. So if I take a look, first I have a network here, the same. I have several CAN transceivers. That's what I'm modeling here. Each one of these would be inside of a controller. I have the CAN bus network over here just modeled with the resistive aspect of it. I don't have any of the capacitance or inductance in the network, just to simplify it so we can see our 220 ohm resistors. Anything where it says CAN high or CAN low, that's where we're headed to. So we've got just basically wire resistance and the resistance of the stubs. So these are 10 thousandths of an ohm of resistance, not very much. We can see, first off, I have this controller. I have it right now set. So in order to provide this bad ground, I have a point here which I've called bad ground, and then I have a point here where I have a series voltage. Now, if I could put a resistor here, but then it would be dependent on the current that this draws as to how much voltage is dropped. I'm going to make this so that it's constant. Obviously, the more current that's carried and you've got a resistance, Ohm's law is going to tell us it's going to drop more voltage on it. So we're going to start off at first as though I don't have a background, and we'll just run through what this looks like. We can see that if I were to check this, I put my voltmeter between this controller's ground and I contact a good ground, and we see what we expect to see, something very close to 0 volts. So we'll go ahead and run the time domain on this first. What I'm going to do is I'm going to turn this, this controller will turn on for 1 bit, will transmit 1 bit, and then I'm going to have this controller transmit 1 bit like 2 microseconds later. So let's take a look at that in the time domain. And here's just exactly what we'd expect it to be. So here's that first controller. I told you we have it so that it has 1 dominant bit. We're transmitting that 1 dominant bit. We then have 2 microseconds where the bus is quiet. And then I have another controller, a different controller, transmitting a bit. Granted, this isn't a real message. We would have more time than that in between, but I'm just using this to illustrate what this looks like. So we can see both of these. If I have these voltage levels drawn, and we'll use this as a reference, we can see where we end up on these. We're like right there. So we'll keep those rulers in place there, and we'll add some resistance to this ground circuit. So I'm going to go ahead. Let's say that I drop 2 volts on this ground circuit. If I look at this now, if I check it with my multimeter, we can see that the multimeter between this point of the ground and a good ground, what we call our bad ground and a good ground, I have 2 volts dropped across it. All I'm really doing is measuring the parallel voltage here at this point. So I'm measuring what this voltage drop is. So think of this voltage as a resistance. It's something where I've got a current flowing through it and it's dropped 2 volts on it. Now, let's see what that looks like when we run our time domain situation. And I think it's going to be surprising to you. Here's what we get. So this is the first controller. Let's go ahead and hide this VDIF. So I have the first controller. We can see where we had our logic levels before. They were down here. We can see that we have moved the voltage higher on that first controller whenever it is transmitting a dominant bit. So CAN high is shown in the blue, is much higher, as is CAN low. However, I've got about the same amount of voltage differential. So in this case, it still works. We're able to see it. I'll go ahead and we'll turn VDIF back on, and we can see that I've got about the same level of difference in voltage here. I've got a good 2 volts difference. So this is well within the threshold of where I would see this as being a dominant bit. Once again, we go back to the recessive bit, and we're sitting at 0. Taking a look at the other controller, the one on the right there, as it's transmitted the 1 bit, it's pretty close to where it was before. All we've done is we've shifted this 0 bias up slightly, and that's one of the things you're going to see on the oscilloscope. So you're going to see this when the controller that has the bad ground transmits, and then you're going to see everybody else's level elevated for the offset, for the 0. It won't be 2.5 volts. In this case, it's 2.7 volts. A lot of guys that troubleshoot with a multimeter only, they are devout, I will never use an oscilloscope crowd, and I know plenty of them from the former employer that I used to work for a few months ago. Lots of guys that work for them wouldn't touch an oscilloscope. I've been told I can troubleshoot anything I need with I'll say this, a Harbor Freight multimeter, if you know what that is. So some cheap multimeter, they feel that they can diagnose anything. And oftentimes I can't disagree with results. They can, but they're doing it in what I would see as a very painful way. They're looking at this and they're having to memorize it. It's like when I see a higher voltage like this, I know I have a bad ground. I don't know which controller has a bad ground. We can tell if we have the oscilloscope, but just looking at this with a multimeter, I would see this kind of a voltage for the offset. So my voltages are going to be elevated at the 9-pin with my Harbor Freight multimeter. I'm going to see a higher voltage at that 9-pin than I would see if I don't have a bad ground. So those are one of the manifestations. I will say one other thing about grounds before I'll go ahead and get rid of this. This ground point is not the same throughout a vehicle, especially something like a larger machine. The larger the machine, I mean, what are we doing? I mean, we're finding a point where it's grounded over here, over there. When the engine is not running, the point of the lowest voltage on the machine is right at the battery negative terminal. When the engine is running, the point that is the lowest, it would be the alternators, the ground, or the reference, the minus output terminal, which is typically the ground, the case of the alternator when the machine is running. So there's even a slight difference in that, and it transfers, if you would, from it's at the batteries or it's at the alternator. So you can do this. You can take a multimeter and move it around through the machine, reference it to some point. You're going to see a difference. So there is no constant to where I'm going to have an exactly 0-volt reference with ground. A lot of manufacturers will want you to ground everything to one point for all the engine controls, say, or they have other places where you want to get all the grounds that you can at that one point. That's the reason for that. We can hold it at that one point. But if you've got grounds all over the machine, and especially if you throw something like an implement into this, where you're depending on the ground of it back through the machine. So whatever you're pulling with a tractor, for example, and it has CAN on it through, say, the ISO bus, you're going to see, don't be surprised, you see a very big shift in the difference between the grounds. So on a tractor, something like a farm tractor, large one, you might see half a volt difference in the ground throughout the machine. And so if I have a controller that is grounded someplace, and especially if somebody has decided I'm going to add this on, and I'm going to put a screw someplace through some sheet metal, and I'm going to say this is the ground for this controller. Okay, it'll probably work, but you're probably going to see this shift. So don't expect to see no shift. This is some of the reason that you might go from one machine to another and see a slightly different voltage. Oftentimes it's because of this difference in ground. Okay, we'll go ahead and we're going to make this a little bit more pronounced. I'm going to change this from 2 volts. Let's get a little more ridiculous. We're going to say that it's got 3 volts. So that's typically, this controller is not going to function. Maybe, depends on how much current it draws. And so this voltage drop depends on the current, and this may be very dynamic, meaning it's changing, and it isn't a constant because it depends, if it's resistive, how much current do I have flowing through it. The more current you flow through it, the higher this voltage drop is going to be. Let's go ahead and take a look to see what this does to our time domain situation. And we can see here, this seems like it looks pretty bad. However, if you look at the difference in voltage, we're still there. We're still at the 2.5 volts. This is probably going to work. It probably will not cause, there's a good chance it will not cause a CAN problem. Granted, this controller, if it's got 3 volts less than it's supposed to have, and there's a good chance that it might not function correctly. It may still function. It just might not function correctly. And you can't, one thing you'll find, you can't run current through a bad resistance for very long without changing it. What does it do? Well, it heats up and it starts to, whatever the connector is, we start to melt, we start to arc. It changes. So this is one of the things you could do with this. If I don't know which controller it is that has this bad ground, I really can't tell off of looking at this. So I can't look at this time domain situation unless I know which controller this is, who's causing the problem. Well, The one way you could do it is you could go around and start disconnecting controllers. And if I have my multimeter and I'm looking right now at my multimeter, my voltages are going to be a lot higher there. I'm not seeing that 2.5, 2.6 or whatever everybody expects to see, 2.7 on KNI. It's probably going to be a lot higher than that average, because look at this average now. I got to throw that 3 volts that I dropped on the ground. That is here. I'm measuring that. And so this will elevate can high. We got an average, and it will elevate can low. So both of those will be higher if I have that controller. Now, granted, I could go through and I could start disconnecting controllers, and once I see those voltages in my multimeter drop back down, I fix it. That's great, but if I've got 50 controllers on this machine, it really makes it hard. Let's say they don't have 50. That's defeating the 1939 standard. We'll say 20 some controllers that I have on this machine. It really makes it hard, especially where I've got to get to each one of these and try to disconnect it. I could spend a substantial amount of time. So let's look at the oscilloscope and see if there's an easier way that we can do that. So here I'm connected to a 250K CAN bus. I'm going to go ahead and stop here. We'll take a look at it. This in particular is not your typical CAN bus. This is I'll call it the after treatment bus. So this is this would consist of controllers such as urea quality sensor, or so a combination of the sensor that's in the DEF tank. So urea quality, temperature, and level. So it would be giving that information over CAN. We also have temperature sensors in this case. So this particular manufacturer, the temperature sensors are on CAN. So I have a couple of different modules. One would be for the SCR temp, one would be for the DOC DPF temperatures. So thermocouples that go into a smart module, and then they put that on CAN. It also has 2 NOx sensors, as well as a VGT turbo. So this is we call it I'll call it an after treatment bus. It does have the turbo on it. It's really not the after treatment, but we'll just refer to it as the after treatment bus. As I indicated, it's a 250K CAN bus. So if I look at, I can see the source address of the controllers that are there on the bus. We can go ahead and we'll let this run for a second, and we can take a look at a whole bunch of these controllers. So if we look, here's a message from the engine. And so as we go through, we have oh my God, there's this great big giant bit at the end. And I've seen somebody recently on a social media talking about, somebody had put this can trace on here, and he said, oh, there's a problem because there's this big spike at the end. And what he's seeing, if you know this is the acknowledge bit. So we have many controllers as they indicate who's on this CAN bus. There's a bunch of controllers that are out there, so we have an acknowledge bit. So this looks pretty reasonable. We have our voltage level. You can see that we're sitting here. Let's see if we can get a ruler here. We get a ruler, and we're sitting at about 2.5 volts for the zero crossing. If we look at what we have for, we're at about 3.4. And we're at about 1.6 or so. And if I look at all of we'll go ahead and look at everything. Everything is at about that range. We do have some noise, and this is just typical. There isn't really anything wrong here. And this is another one of those things. If you look right here, I have the A minus B. So you can see that there's a big spike here. And this spike really isn't causing any problem. I'm not even going to try to figure out what this is. This is a engine controller system that I have sitting on my bench. I have a workbench that I have all this laid out. I've got some place where I'm inducing a voltage, but the voltage is being induced both in CAN high and CAN low, and I know that because the A minus B is showing me that I have nothing. So would I troubleshoot this? I could, but I'm not going to waste my time. I really don't care. CAN is so robust that it's able to handle this. This is probably some of the wiring that I've got laying on my bench. I've done some things that I probably that I wouldn't begin to do on a real vehicle or a real machine, but on my bench, it's here. I'm not worried about it. As we've indicated before, I mean, you can see right here, we don't really care about this. It doesn't even exist. It's common mode. So it's both on CAN high and CAN low. We look at high minus low is what we're looking at. And this is one of the great things about CAN. You can see right here, whatever this noise is that we're getting, I suspect I have this ling out. I really don't know exactly what this is. I could go troubleshoot it. I'm not going to waste my time. I don't care. So I'm going to go ahead and I'm going to add some resistance to the ground. You can see what this looks like right now. Once again, we don't freak out over these little voltage spikes that we have over here and there. They're not causing us a problem. We have some oscillation here where it's off. I've got something. I mean, these aren't canceling each other out perfectly, and so I have some of these spikes. Big deal. CAN is able to handle this. Don't go running after something like this. Don't chase after something. But I'm going to show you what the bad ground looks like. That is something you want to chase after. Let me go ahead and set that up. Okay, I've introduced a bad ground on one of my smart sensors. So we can take a look at what we have on the bus. We can see that we know source address is 0 is the engine controller. So the engine controller, the voltages look, they're higher. As I said before, we're going to see this elevation. We're a little above the 2.5 volts now. Where are we at? We're at about 2.75, 2.8 volts or so. We can see that we are a little higher, 3.7. We're also a little bit higher than we typically are on CAN low. So it doesn't go as low. So we're offset there a little bit. Let's take a look as the effect becomes more pronounced when we go to the offending sensor, the device which has the problem. And if we take a look and we zoom in on this, we can see we're still getting data. We can see that we have this message from this case source address 51. Granted, I've went so high that I've exceeded my 5 volts. This is something here has a problem. It's this device apparently, and whatever source address 51. Here's something I'm going to tell you. Source address 51 is the inlet NOx sensor. So this is designated as the NOx sensor. The outlet would be source address 52. This is in hexadecimal. You don't know this information probably because you don't have the SAE J1939 specification. You don't have enough service information to allow you to troubleshoot at this level. So here's my kind of recommendation. If you work for a manufacturer, you ought to ask them why they're not giving you this information. This isn't anything that's top secret or proprietary. It's out there. It's J1939. It's published. It's throughout the industry. Every inlet NOx sensor is going to have this source address of 51. That's on a heavy duty diesel. So this isn't anything that's not information that you shouldn't have. So if I knew that this is the inlet NOx sensor, I don't have to go around and disconnect a bunch of controllers, but I will. We'll go ahead and watch what happens. I'm going to put this on here. We'll let it run. And we can see this is what my bus looks like. It looks bad. Even though it still works, I'll go ahead and I'll disconnect the offending controller. Disconnected the inlet NOx sensor, and you can see now our data looks good. I could have spent an hour going around this machine and disconnecting every controller, trying to find out which one has this bad ground. Granted, this NOx sensor probably wouldn't have worked. The NOx sensors have a heater which are required for it to work. I don't have the engine running or simulator running right now, so the heater's not on. But the device may still function, or it may function for a while until I turn that heater on, and then you've got this intermittent problem. You may have a fault that come in there for it. You may not have a fault code for any of this. So if you had the oscilloscope, you had the ability to look at this information, something that can decode it, such as this picoscope that I have, and there's other manufacturers that isn't just theirs, but this is one that I've come accustomed to using. I can look at this information and see that source address 51 was my problem. 52 is here as the outlet NOx sensor. It looks fine. I don't have any trouble with it. You can see that my data now looks clean. I don't have any problems anymore. The ground that I had on that sensor, I'm actually able to diagnose this isn't a bad sensor. This is just a bad ground. So you can troubleshoot things by going around and disconnecting stuff until it looks right and spend who knows how much time doing that. Or if you had the information, if you're a manufacturer, if you work for a manufacturer, if they provided you that information, you could go diagnose this yourself. I am serious about this thing that the manufacturers of who you work for should be giving you more information. If they expect you to be able to diagnose these complex machines, and they're doing nothing other than getting more and more complicated. If CAN looks hard, wait till you see Ethernet. I guess I'll do one more episode, and I'll cover some really cool tools that are there that I use as an engineer. Some things that you'll be envious of, but once again, you got to have the information. It's just kind of to show you some of the things, the background. If you ever decide I'm tired of being a technician and I want to be an engineer, you could do like I did, and you could make that transition. And then maybe one of these days you can create a series of videos or whatever the technology is in the future for techs that are in the field.